NENOMATICA, where mathematics meets YouTube excellence. Welcome to this mathematics video where we'll explore the difference of squares identity and learn how to apply it to factorize expressions. The difference of squares identity is a fundamental algebraic formula that helps us factor expressions where one term is being subtracted from another, and both terms are perfect squares. This identity states that a squared minus b squared equals a minus b times a plus b. Our first example is x squared minus 9. First, we need to identify the perfect squares in this expression. X squared is already a perfect square, where it equals x. And 9 is also a perfect square, since 9 equals 3 squared. So b equals 3. Now we can apply the difference of squares identity. A squared minus b squared equals a minus b times a plus b. Substituting our values, we get x squared minus 3 squared equals x minus 3 times x plus 3. So x squared minus 9 equals x minus 3 times x plus 3. This is our factorized form. Let's look at another example. This time, we have 4x squared minus y squared. Again, we first identify the perfect squares. The first term is 4x squared, which is equal to 2x squared. So iguals 2x. The second term is y squared, so b equals y. Applying the difference of squares identity, we substitute at equals 2x and b equals y into our identity formula. So 4x squared minus y squared equals 2x minus y times 2x plus y. Therefore, 4x squared minus y squared equals 2x minus y times 2x plus y. Let's try one more example, this time with a more complex expression x to the fourth power minus 25. First, we need to identify if this fits the difference of squares pattern. X to the fourth power can be written as x squared squared. So equals x squared. And 25 equals 5 squared. So b equals 5. Applying the difference of squares identity, x to the fourth power minus 25 equals x squared minus 5 times x squared plus 5. But wait, we're not done yet. The first factor, x squared minus 5, doesn't factorize further because 5 is not a perfect square. However, the second factor, x squared plus 5, also cannot be factorized further over the real numbers because it's a sum of squares. Therefore, our final factorization is x to the fourth power minus 25 equals x squared minus 5 times x squared plus 5. Let's summarize what we've learned about the difference of squares identity. The difference of squares identity states that a squared minus b squared equals a minus b times a plus b. This is a powerful factorization technique that helps us simplify expressions. We've seen 3 examples. First, x squared minus 9, which factorizes to x minus 3 times x plus 3. Second, for x squared minus y squared, which factorizes to 2x minus y times 2x plus y. And third, x to the fourth power minus 25, which factorizes to x squared minus 5 times x squared plus 5. For practice, try factorizing these expressions on your own, 16 minus t squared and p squared q squared minus 4. Now, let's look at some examples to better understand how to apply this formula. Our first example is for a squared minus 9b squared. First, we need to identify what a and b are in this expression. We can rewrite this as the square of 2 a minus the square of 3b. So a equals 2a and b equals 3b. Applying our formula, we get 2a plus 3b times 2a minus 3b. Let's look at our second example from the image. We have 4x squared minus 9. Let's identify a and b. We can rewrite this as the square of 2x minus the square of 3. So it equals 2x and b equals 3. Applying our formula, we get 2x plus 3 times 2x minus 3. Remember to identify what a and b are in your expression, then apply the formula. This technique is especially useful when you have perfect squares being subtracted from each other. Practice this technique with various examples to become proficient at recognizing and applying it. We want to factor x to the 8th minus 1. Step 1. Let's recognize that x to the 8th minus 1 can be viewed as a difference of squares. Remember, the difference of squares formula tells us that a squared minus b squared equals a minus b times a plus b. In our case, we can rewrite x to the 8th as x to the 4th squared. So our expression becomes x to the 4th squared minus 1 squared. Step 2. Now, let's apply the difference of squares formula. We get x to the fourth minus 1 times x to the fourth plus 1. Step 3. Let's focus on the first factor, x to the fourth minus 1. We can factor this further using the same difference of squares formula. X to the fourth minus 1 can be written as x squared squared minus 1 squared. Applying the difference of squares formula, we get x squared minus 1 times x squared plus 1. Step 4. We can factor x squared minus 1 further, as it's also a difference of squares. X squared minus 1 equals x squared minus 1 squared. Applying the difference of squares one more time, we get x minus 1 times x plus 1. Step 5. Now, let's combine all our factors to get the complete factorization. We have x minus 1 times x plus 1 from factoring x squared minus 1. We also have x squared plus 1 from factoring x to the fourth minus 1. And finally, we have x to the fourth plus 1 from our initial factorization. So, the complete factorization of x to the eighth minus 1 is x minus 1 times x plus 1 times x squared plus 1 times x to the fourth plus 1. Let's take a look at an example. We want to factor the polynomial x to the power of 4 plus 2x cubed minus 7x squared minus 8x plus 12. Step 1. Let's start by grouping the terms. We'll group the terms with even powers together and the terms with odd powers together. Step 2. Now, let's work on factoring each of these groups. For the first group, we can see that it contains terms with only even powers of x. The second group has a common factor of 2x. Step 3. Let's look at the first group more closely. If we let u equal x squared, we get u squared minus 7u plus 12, which we can factor as u minus 3 times u minus 4. Then substituting back x squared for u, we get x squared minus 3 times x squared minus 4. Step 4. Now let's look at both groups. We notice that x squared minus 4 is a common factor. We can factor it out to get x squared minus 4 times x squared minus 3 plus 2x. Step 5. We can factor these expressions further. X squared minus 4 can be written as x minus 2 times x plus 2, since it's a difference of squares. And x squared plus 2x minus 3 can be factored as x plus 3 times x minus 1, using the quadratic formula or by finding two numbers that multiply to negative 3 and add up to positive 2. Therefore, the complete factorization of our polynomial x to the power of 4 plus 2x cubed minus 7x squared minus 8x plus 12 is x minus 2 times x plus 2 times x plus 3 times x minus 1. We can verify this is correct by multiplying these factors together, which would give us back our original polynomial. Let's summarize the factoring techniques we used. First, we grouped terms to isolate common factors. Then, we used substitution to make factoring easier. We factored out common terms when possible. We used the difference of squares formula. A squared minus b squared equals a minus b times a plus b. And finally, we factored quadratic expressions by finding values that satisfy the correct sum and product. These techniques can be applied to factor many different types of polynomials. Let's start with our example problem. We need to simplify the following expression: a squared plus 1 squared minus a squared minus 2a minus 1. First, let's expand this expression by rearranging terms. We notice that a squared plus 2a plus 1 can be rewritten as a plus 1 squared. So we can rewrite our expression as a squared plus 1 squared minus a squared plus 2a plus 1. In the second step, we recognize that a squared plus 2a plus 1 is equal to a plus 1 squared. So our expression becomes a squared plus 1 squared minus a plus 1 squared. For step 3, we'll apply the difference of squares formula. We have a squared plus 1 plus a plus 1 multiplied by a squared plus 1 minus a plus 1. In step 4, we simplify the factored form. In the first factor, we get a squared plus a plus 2, and in the second factor, we get a squared minus a. This gives us a squared plus a plus 2 times a squared minus a. For our final step, we notice that in the second factor, a squared minus a, we can factor out a common a. This gives us a times a minus 1. Our expression becomes a times a squared plus a plus 2 times a minus 1. So our final answer is a times a squared plus a plus 2 times a minus 1. Let's quickly verify this is correct by expanding it back and checking against our original expression. In summary, we've transformed the expression, a squared plus 1 squared minus a squared minus 2 a minus 1 into a factored form, a times a squared plus a plus 2 times a minus 1. We did this by first rewriting the expression in terms of perfect squares, then applying the difference of squares formula, and finally factoring out common terms. These algebraic techniques are useful for simplifying complex expressions and solving equations. For practice, try factoring similar expressions like a squared minus 1 squared minus a squared plus 2a minus 1. Welcome to this math tutorial. Today, we're going to learn how to factor the difference of powers. Specifically, we'll work through the factorization of x to the power of 2 to the power of 7 minus y to the power of 2 to the power of 7. Let's start with our expression x to the power of 2 to the power of 7 minus y to the power of 2 to the power of 7. First, we'll calculate what 2 to the power of 7 equals. 2 to the power of 7 equals 128. So our expression is x to the power of 128 minus y to the power of 128. Now, we can apply the difference of powers formula to factor this expression. The formula states that a to the power of n minus b to the power of n equals the product of a minus b, and the sum a to the power of n minus 1 plus a to the power of n minus 2 times b, and so on until b to the power of n minus 1. In our case, we'll use a special case of this formula where n equals 2. So x to the power of 128 minus y to the power of 128 equals the product of x to the power of 64 minus y to the power of 64 and x to the power of 64 plus y to the power of 64. Let's continue by applying the same formula to the first factor. We get x to the power of 64 minus y to the power of 64 equals x to the power of 32 minus y to the power of 32 times x to the power of 32 plus y to the power of 32. We'll continue this process. For the term x to the power of 32 minus y to the power of 32, we apply the formula again to get x to the power of 16 minus y to the power of 16 times x to the power of 16 plus y to the power of 16. We continue applying the formula to the term x to the power of 16 minus y to the power of 16, which gives us x to the power of 8 minus y to the power of 8 times x to the power of 8 plus y to the power of 8. Next, we apply the formula to x to the power of 8 minus y to the power of 8, getting x to the power of 4 minus y to the power of 4 times x to the power of 4 plus y to the power of 4. For x to the power of 4 minus y to the power of 4, we apply the formula to get x squared minus y squared times x squared plus y squared. Finally, we apply the formula to x squared minus y squared, which gives us x minus y times x plus y. Let's summarize what we've done. We started with the expression x to the power of 2 to the power of 7 minus y to the power of 2 to the power of 7, which is x to the power of 128 minus y to the power of 128. By repeatedly applying the difference of powers formula, we factored this expression into a product of 8 factors x minus y, x plus y, x squared plus y squared, x to the power of 4 plus y to the power of 4, x to the power of 8 plus y to the power of 8, x to the power of 16 plus y to the power of 16, x to the power of 32 plus y to the power of 32, and x to the power of 64 plus y to the power of 64. This is our final answer. This technique of repeatedly applying the difference of powers formula is a powerful way to factor expressions involving high powers. The key is to recognize the pattern and apply the formula step by step. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.